Hi everyone, this is supposed to be the first of a series of videos that I would like to make under the title of Differential Calculus with Python. Well, because I'm quite forgetful, so I have noted down the steps of presentation here. The first thing I would like to present is ReLU prime of 0. What is its value? So this is the graph of the ReLU function. As you can see, at x equals 0, ReLU is not differentiable. Why would we be interested in answering ReLU prime of 0? Well, ReLU is a quite commonly used activation function by deep learning practitioners. And in deep learning, we do gradient descent. So it would be weird if we do not know how to differentiate or how to calculate the gradient of the ReLU function. Yeah. I have also plotted other activation functions like leaky ReLU, which is also not differentiable at 0. And also there is ReLU, Swish, and Sub Plus. Some people tend to think of these three functions as a smooth version of the ReLU function, in the sense that their shape are all close to the ReLU function. Okay. Yeah, but there might be some people that have opposing arguments with me. They would say that like this, let's not worry about ReLU prime 0 because that's just a single point, and if we randomly initialize the weight of a neural network and the data is also random enough, then the probability for a neuron to fall into the point 0 is nearly 0, or with a very, very low probability. So nearly never happen. We don't need to worry about it. Well, I'm not going to deal with this argument for now. I plan to deal with it in part 3 of the series. For the moment, I want to proceed to a theory that deals with ReLU prime 0. Like it doesn't avoid the problem. So what is a subgradient? Well, we can read the definition. So basically, subgradient is what you will put up with or satisfy yourself with when you cannot find the gradient. Yeah. So the setting is pretty much the same as the setting when we want to find a gradient. The objective function f will be from Rn to R, and here we assume it to be convex, and then a vector in Rn is said to be a gradient of f at a point x0 if the value of f at any other point will be greater than or equal to f of x0 plus the inner product of g and x minus x0. Yeah. So put more simply, using this example, the ReLU function is from R to R. Then this simply means that a slope or a real value is a subgradient of the ReLU function at x equals 0 if the straight line passes through 0, 0 and lies entirely beneath the blue line, the objective function f. Yeah. So in this example, when the slope equals 0.8 or 0.7, it is a subgradient. And as we increase it, 0.8, 0.9, it is still a subgradient. Even when it equals 1.0, it is a subgradient. But when we go one step further, 1.1, it is no longer a subgradient because the part right to x equals 0 goes beyond the blue curve. Yeah. So these are not subgradient anymore. Yeah. And if we go into the opposite direction, it's kind of the same story. Will be subgradient, yeah, until the straight line goes and assumes a horizontal position. It is still a subgradient, and then minus 0.1 is no longer a subgradient for the same reason we just stated. Yeah. So the theory of subgradient methods is just that we try to descend with subgradient, any of the subgradient instead of a gradient, because we cannot find a gradient, and we try to develop a valid theory of minimization or maximization. Yeah. We won't go into the detail. We will just stop here in our introduction to subgradient methods. If those of you who haven't heard of subgradient methods and would like to dig in deeper, I've joined a few links here so that you can check them out. Next, we will move on to exploring how PyTorch deal with ReLU prime of 0. PyTorch must be able to deal with ReLU prime of 0, otherwise, because this is too small a question, so yeah, it is impossible that PyTorch cannot deal with this. So the question is how it deals with it. Yeah. And sorry, let's open up this link. If one is interested in this kind of question, sooner or later one will bump into this article by PyTorch called Autograph Mechanics, and in one of its sections they wrote how gradients for non-differential functions are calculated. Yeah, since it's not differentiable anymore, so we must have something to replace the gradient. And in the second and third point, it stated the situation when the function is convex and when the function is concave. Yeah. So let's read the second point. For example, if the function is convex, then PyTorch will use the subgradient of minimum norm. So we see that PyTorch actually uses subgradient, and but which subgradient? It uses the subgradient of minimum norm. Yeah. You might, some might wonder, we have introduced the concept of subgradient, but we did not specify the norm. Subgradient is a vector in Rn. So in Rn, we know there are many norms. So which norm does it refer to here? Actually, if you think about it, the subgradients of minimum norm will be of minimum norm no matter what norm you use. Yeah. Okay, so now what I would like to do is I'll state the third point. The third point simply states that when the function is concave, then PyTorch will use the supergradient of minimum norm. So it's quite similar. And supergradient is just that when the function is concave, we will have something like a global bound for the function, instead of for in the case of subgradient is something below the graph of the function f. Yeah. Okay, now I would like to try to verify these two statements in Python using a Colab notebook. Yeah. But first, I would like to recall how PyTorch do differentiation, or how PyTorch calculates gradients. So normally we will have a function, say exponential, say sine, for example, and then we'll have a point at which we would like to differentiate. Say how much? I don't know, 1.7. And in PyTorch we have to use this required grad so that we can track the variable x0 when we do backpropagation, or when we do calculate the gradient. Okay, now we compute a scalar value y, which equals f of x0. Next we call the backward method. This step is the differentiation. After this step, we can infer the gradient or the derivative. Yeah. So here the derivative will be x0 grad, x0 dot grad, and to print it more beautifully, we would go like this. No, sorry. Okay. On the other hand, we also know that cosine functions derivative is sine functions derivative is cosine. So let's check cosine x0 should be equal to that cosine x0. Okay, that's verified. Yeah, great. So this is how we do simple derivative calculation in PyTorch, and with this we can already check what PyTorch calculate, what's ReLU prime of 0 according to PyTorch. So we make the function ReLU, we make the point 0.0. Yeah, so we'll see. So we'll see that it gives the answer of 0. So ReLU takes the subgradient of 0 as ReLU prime of 0. Yeah. And indeed, we see that 0 is indeed a subgradient for the ReLU function at x equals 0, and In this case, the norm of a subgradient is simply the absolute value of the slope, and 0 is indeed the one with the minimum norm. So we have verified that the second point, the second statement is at least correct for the convex function here, the ReLU function. Yeah. Actually, I have written a better notebook to visualize this. So let's import the packages that we need. And this function is a helper function to help me plot when we input a function f and a point of differentiation at which we differentiate. It will try to plot the function like around the point of differentiation, and also plots the tangent to the point whose derivative is given by PyTorch. Yeah. So let's run this. So for example, if we give it cosine at 2.7, it will try to plot like this. And now we'll try the question we are interested in, that is ReLU prime of 0. So it will visualize ReLU prime of 0, telling us which subgradient PyTorch chooses, and here PyTorch chooses the subgradient with a slope equals 0. Yeah. Actually, the absolute value function is another convex function, so we can try to run with the absolute value function as the non-differentiability x equals 0, and try to see what PyTorch gives as a subgradient. So in this case, it also gives the horizontal line as the subgradient. Yeah, and it is indeed also the subgradient of minimum norm. So the second point in the autograph mechanics is verified, at least for these two functions. Now let's move on to concave functions. That is the third statement. It says that if the function is concave, then PyTorch will use the supergradient of minimum norm. For a simple concave function, we'll simply choose a piecewise linear function, and here we choose the leaky ReLU. We have introduced the leaky ReLU here. It is like this. Yeah, like this. And in PyTorch, we can control the left slope. That is the slope of the left line. Yeah, we have a control of its slope. So as the slope gets bigger and bigger, when it gets bigger than 1, the graph will become concave, and we will see when it gets concave what is the subgradient that PyTorch gives. So here is another visualization function that I implemented. This simply does the same thing as above, except that it here the function is fixed to be leaky ReLU. What is tunable is the left slope, and using it along with the IPy widget, we can have an interactive visualization. Yeah. So let's run it. Take some time. Let's wait for it. Okay, so we have this left slope slider here, which we can adjust. So we just said that we will increase the left slope until it is greater than 1, so that the graph becomes concave like this. So we see that here PyTorch gives the subgradient at this point 0, 0 as the left slope. Yeah. But if you if you are careful, you will find that actually this is not the subgradient of minimum norm here, because it's not a supergradient of minimum norm, excuse me, but the one with minimum norm will be the slope of 1, the slope that equals 1. Yeah, so it'd be like this instead of like the red dashed line. Yeah, so I want to say that at least we found a counterexample which invalidates the third statement. So it is not always the supergradient of minimum norm. Yeah. Yeah. So here, naturally, one might wonder whether PyTorch developers they implement a convexity check, so that every time when we encounter a non-differentiable point, we check whether the function is convex or concave, and we follow the principle, the second or the third principle, like this. Yeah. In order to know whether this is true, whether there exists a convexity check in the source code, we have to check the source code. Yeah. But before diving into the source code, a quick answer for this is that no, PyTorch developers does not implement a convexity check. Yeah. Okay. And now let's go to the PyTorch source code, and in particular we'll go into tools autograd and then derivatives.yaml. Yeah. And in this file, on top of the file there is a long explanation of for the file. I think we'll skip it because we don't have that much time. And as you can see, the first function in this file, it defines a lot of functions and their gradients, how to calculate their gradients. The function name is described in the name, and the gradient is described in this self thing. Okay, so maybe let's look at some simple functions like sine, cosine. Yeah, here's the sine function. So it's here. The sine function, it has a gradient of grad times self.cosine.conj. Yeah. So we see that at least something familiar pops out. It is cosine. which is indeed the derivative of the sine function. Yeah, just that we haven't already know what grad means and what conj means. Yeah, actually we would tend to guess that conj is the conjugate for a complex number, and indeed it is a conjugate. But this part involves this part is more involved, so I decided not to touch this until the second video of this series. Yeah, and the grad is actually, it means it's like a chain rule. When you have your sine function inside another function, you'll have the derivative of that function multiplied by the derivative of the sine function. Here, the grad simply means that. Yeah. So let's go back to our notes. So actually, I have written here down the notes. So there is sine and there is cosine. Cosine will be grad times minus sine dot conj, and exponential will be simply grad times result dot conj. Yeah. So actually, this is quite readable, but for some functions like ReLU, it is harder to understand. But if you spend enough time, you will see that PyTorch defines ReLU prime of x equals 0 when x equals 0, and every other point will be normally just the gradients. Yeah, and also if you try to understand the source code, absolute prime of x equals this. It equals 0 when x equals 0. Yeah, and the other part are just normal, 1 here and minus 1 here. Yeah. So actually, it is not very easy to find your answer in the source code, and there's a fun fact. Even Andrei Karpathy found it so too. I mean, even Andrei Karpathy felt it difficult to locate the exact source code. How do I know? Because in this YouTube video from Andrei Karpathy, it introduces AutoGrad, in particular a library he wrote by himself, micrograd. At the end of the video, it mentions that he tried to demonstrate or show how PyTorch implements their AutoGrad, but he cannot seem to find quickly what he wants. Yeah. So if you want to find something in PyTorch source code and you cannot make it in a short time, don't feel frustrated. It's actually quite normal. You can simply search instead on the PyTorch forum here, or if you can't find anything, just try to ask a new question. Like me for this video, for the preparation, or not for a preparation, because at first this is my own question, my own quest. It is thanks to Alban D on the forum who helped me successfully located the file derivatives.yaml. If it's not him, I wouldn't know to look into this file. Yeah. So conclusion. ReLU Prime 0 PyTorch knows how to do it. PyTorch indeed deals with it, and PyTorch developers are well aware of subgradient methods. But the usual way one constructs deep neural network and one do gradient descent, even with any other how do you say that, atom or any other gradient descent methods, we're not using subgradient methods. But this does not mean that PyTorch is incapable of implementing subgradient method. It just means that if you want to stick closely to subgradient method, you'll have to write your own code. The normal way you do gradient descent in deep learning, it is not strictly subgradient methods. And also, we're also seeing that in the case of leaky ReLU, the case of concave function, the principle stated in the autograph mechanics article is not closely followed. It may differ. And in the source code, we also see that it is not through a convexity check that it decides, okay, I should follow principle 2 or principle 3 of the article. No, it is somewhat like hard-coded into the YAML file, and then it will follow the hard-coded rules in those files. Yeah. Okay. I think this is the end of the first video. See you another time. Bye bye.